Hello students, I am Dr.A.Muthuselvi, Assistant Professor of Mathematics from the Standard Fireworks Rajaratnam College for Women, Sivakasi. So in this topic we will discuss about the span of a set. First of all, we shall discuss what is the span of a set and and its some results, also discuss about some examples. First definition, spanning sets. So before we enter the topic, we define the linear combination definition. A vector u in a vector space V is called a linear combinations of the vectors v1, v2, etc. vk in V if u can be written in the form, that is u equal to c1 v1 plus c2 v2 plus etc. ck vk, where c1 c2 etc. ck are real number scalars. Some examples. Finding a linear combination. Here the values of v1, v2, v3 are given. We have to prove w is, first one is a linear combination of v1, v2, v3, and the second one is not a linear combination of v1, v2, v3. First we take w equal to c1 v1 plus c2 v2 plus c3 v3. So here we substitute the values of w, v1, v2 and v3. So we get 1, 1, 1 equal to c1 into 1, 2, 3 plus c2 into 0, 1, 2 plus c3 into minus 1, 0, 1. So we substitute the values in the matrix form and the row using the operations row and column. We reduced the above matrix into upper triangular matrix. So we get C3 equal to T, substitute the value in C3 in the previous two equations, we get C1 and C2 values. We substitute T values, we have lot of solutions. For example, T equal to 0, 1, 2 up to etc. So this system has infinitely many solutions. Second one, here W value is W equal to 1, minus 2, 2. First of all, we take the linear combination W equal to C1 V1 plus C2 V2 plus C3 V3. Next, the system of equations can be reduced into matrix form, and also we do some row and column operations to reduce the given matrix into upper triangular matrix. Here we have the equation 0 into C1 plus 0 into C2 plus 0 into C3 equal to 7. This is not a valid equation because the right side value is 7 but the left side is we have 0. So W cannot be expressed as C1 V1 plus C2 V2 plus C3 V3. Next we enter into the definition, the span of a set. So the notation is span of S. If S equal to V1 vectors, V1, V2, etc., Vk is a set of vectors in a vector space V, then the set of all linear combinations of finite sets of elements of S is called a linear span of S and is denoted by L of S. So any element of L of S is of the form span of S equal to set of all C1 V1 plus C2 V2 plus etc. Ck Vk for all Ci belongs to R. That is the set of all linear combinations of vectors in S is denoted by L of S. Next one, definition of a spanning set of a vector space. If every vector in a given vector space V can be written as a linear combination of vectors in a set S, then the set S is called a spanning set of the vector space V. That is, every vectors in the vector space is formed by the span set. So the span of S is can be generated, can be expressed as follows. That is, span of S equal to V, or otherwise S spans generates V, otherwise V is spanned by S, or S is spanning set of V. Next example, the set S equal to set of all vectors spans R power 3 because R3 because any vector U equal to U1, U2, U3 in R3 can be written as U1 equal to, that is linear combination. Here we substitute the given scalar values in the scalar places. So u equal to U1 into 1 comma 0 comma 0 plus u2 into 0 comma 1 comma 0 plus u3 into 0 comma 0 comma 1. Also the next example can be written as in the polynomial function. A spanning set for R3. Show that the set S equal to set of all scalars spans in R3. We determine whether an arbitrary vector u equal to u1, u2, u3 in R3. Expressed as a linear combination of v1 equal to 1, 2, 3, v2 equal to 0, 1, 2 and v3 equal to minus 2, 0, 1. So, we take the linear combination u equal to c1 v1 plus c2 v2 plus c3 v3. We substitute the values of vectors, the given vectors v1, v2, v3. So, we have three equations. We reduce the given equations to find the values of u1, u2, u3. Here we use another method to find the values of u. So, first of all we determine the value of the determinant a. So, here determinant a is not equal to 0, therefore, we know the result ax equal to u has exactly one solution for every u. Therefore, span of S equal to R3. Next one, first theorem. Span of S is a subspace of V. S is a set of all vectors in a vector space V. Then, first one, span of S is a subspace of V. Second one, S is contained in L of S. Third one, span of S is the smallest subspace of V that contains S. That is, every other subspace of V containing S must contain span of S. So, first one, proof. Consider any two vectors. So, in first one we prove span of S is a subspace of V. So, we take one element from span of S. So, here we consider two vectors u and v in, we take two vectors u and v in span of S. We prove this part using one theorem. So, first u can be written in the linear form u equal to c1 v1, c2 v2 plus etc. ck vk and v equal to d1 v1 plus d2 v2 plus etc. dk vk. So, here we add the two vectors u plus v equal to c1 plus d1 into v1 plus c2 plus d2 into v2 plus etc. ck plus dk into vk belongs to span of S. And also we find the scalar multiplication of u. Cu equal to c1 v1 plus cc2 v2 plus etc. cck vk, which is also in span of S, because they can be written as the linear combination of vectors. So, here we using the subspace theorem, that is W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following conditions hold. First one is, if u and v are in the vector space W, then u plus v is in W, that is the vector space. Second one is, if u is in W, that is vector space, and C is any scalar, then Cu is in W. Here the two conditions are satisfied. So, we get the span of S is a subspace of V. So, second part, here second part we prove that we will to prove S is subset of L of S. So, we take one element from S. So, let u belongs to S, that is u taken from S. Then u equal to L into u, which is also in L of S. Hence, S is contained in L of S. Third one, here we will prove span of S is the smallest subspace of V that contains S. So, we take a element u belongs to span of S, that is u equal to linear combination c1 v1 plus c2 v2 plus etc. ck vk, where vi's are vectors and ci's are scalars. U also contains S, that implies vector space Vi which is also in U, since U is a subspace. So U equal to linear combination C1 V1 plus C2 V2 plus etc. Ck Vk, which is also in U, because U is closed under vector addition and scalar multiplication. And also U belongs to span of S, U also belongs to U, which we conclude that span of S contains U, and span of S is the smallest space of V that contains S, which is equal to V1, V2 etc. Vk. Next theorem, let V be a vector space over a field F, let S comma T contained in V, then first one, S is contained in T, which implies L of S, that is span of S is contained in span of T. Second one is span of S union T equal to span of S plus span of T. Third one is span of S is equal to S if and only if S is a subspace of V. So we will take the first one, let S is contained in T, that is S is a subset of T. Let one element, we take one element from L of S, U belongs to L of S, then U equal to C1 V1 plus C2 V2 plus etc. Ck Vk. Vi belongs to S and Ci belongs to in the field F. Since S is contained in T, so Vi's are also belongs to T. Hence C1 V1 plus C2 V2 plus etc. Ck Vk, which is Vi belongs to L of T. Thus L of S is contained in L of T. So second one, we take one element from the left side, U belongs to L of S union T. Then U equal to linear combination, that is C1 V1 plus C2 V2 plus etc. Ck Vk. Vi belongs to S union T and Ci belongs to in the field F. Without loss of generality, we assume that V1 V2 etc. Vm which is belongs to S and Vm plus 1 Vm plus 2 etc. Vk belongs to T. And C1 V1 plus C2 V2 plus etc. Cm Vm belongs to L of S, and Cm plus 1 Vm plus 1 plus etc. Cm plus 2 Vm plus 2 etc. plus Ck Vk belongs to L of T. Thus U equal to C1 V1 plus C2 V2 etc. Cm Vm plus Cm plus 1 Vm plus 1 plus Cm plus 2 Vm plus 2 plus etc. plus Ck Vk belongs to L of S plus L of T. So we prove the one part, that is L of S union T contained in L of S plus L of T. Similarly, we claim that L of S plus L of T is contained in L of S union T. Hence L of S union T equal to L of S plus L of T. Next one, let L of S equal to S. So we prove that S is a subspace of V. By using the above theorem, we obviously get S is a subspace of V. So we will prove the converse part. Let S be a subspace of V. Then the smallest subspace containing S itself. So here we get L of S equal to S. Students, I hope this video is useful to know about the span of a set. Thanks for watching this video.